So the next chapter is capacitor. Definition of the capacitor. An electric device which is used to store electric energy. It is also used in radio, TV, tuning circuits, and smoothing of ripples in alternating, fluctuating electric current or voltage. We have to study parallel plate capacitors. So parallel plate capacitors. It consists of two metal plates which are held parallel to each other with some separation, and this separation is insulator. In A level, this is considered free space or vacuum. And the permittivity of the free space is represented by epsilon naught. Now this A and B are the plates which will store charges. Suppose A stores plus 5 coulomb charge, then the B will store minus 5 coulomb charge. That's why the total charge on the capacitor will be 0 because positive negative cancelled. So we can't say that the capacitor is a device which stores charges, because when it is uncharged, when it is charged, the total resultant charge will be 0. So the plates will store charge, one plate positive, other negative, and the insulator, this insulator will store electric energy. So energy is stored in the insulator, and the charges are stored on the surface of the plate. Next, charging of a capacitor. Suppose we have this parallel plate capacitor. This is also the symbol for the capacitor, two lines of equal length. It is connected with ammeter, then connected with a switch, suppose S, and then connected with a DC power supply, suppose battery. Initially, this capacitor is uncharged, so the potential is 0 volt, and the battery is fully charged. Suppose its potential is 9 volt. So switch is open, no flow of the charge, no current. So the reading of the ammeter is 0 initially. When the switch is closed, due to potential difference, delta V between the battery and the capacitor, which is initially 9 minus 0, 9 volt, charge will flow. So the current will be there in the ammeter. So the current will be greater than 0, mean the current is recorded by the ammeter. Now, this positive plate of the battery is gaining electrons from the plate. So due to the loss of the plate and loss of the electrons from this plate, this will gain positive charge. And this negative terminal of the battery is sending electrons to this plate. So after gaining electron, it is negatively charged. So the positive charge on the A plate and the negative charge on the B plate gradually increasing with the passage of time. But the potential of this battery is decreasing because it's sending its potential, sending its charges to the battery. So the potential of the capacitor is increasing. So the initially 9-volt potential difference, and after some time, this potential difference becomes 8 minus 1, 7 volt, and gradually this potential difference decreases, and finally, when both are at the same potential, suppose this is at 4.5 volt, this is also at the 4.5, then the potential difference 0, no current again. So initial potential difference 9 volt, gradually decreasing, so the current decreasing. So the reading of the ammeter during the charging of the capacitor will go like this. Time at the x-axis, current at the y-axis. So initially the maximum current gradually decreases and finally becomes 0. So this is the reading of the ammeter. So when the current I becomes 0 after some time, so this is the indication that your capacitor is fully charged. When the reading of the ammeter becomes 0, it means the capacitor is fully charged. So initially, when switch is closed, due to large potential difference, initial current will be large and the final current will be 0. Now, the charge is stored by the surface of each plate. So the charge stored by the plate against time. Initially no charge. It gradually increases. When it becomes fully charged, then the charge on the plate becomes constant. And similarly, the potential stored by the capacitor against time, initially uncharged, no potential, potential increases, and finally it becomes 0. Now look at this graph. We have relation Q is equal to IT. It means I is equal to Q divided by T. So the gradient of this graph is electric current. And the area of this graph is equal to charge Q. Then these two graphs for the capacitor, charge on the plate of the capacitor, voltage on the capacitor, look at them, 0, so voltage 0. Charge increasing, voltage increasing. Charge becomes constant, voltage becomes constant. So we can write charge of the capacitor and voltage, both are directly proportional to each other. So Q directly proportional V mean if the graph is plotted between potential of the capacitor and the charge in coulomb of one of the plate of the capacitor, then both are directly proportional, means straight line passing through the origin. Now this equation can be written as Q is equal to some constant into V, but here constant is C into V. And this C constant is known as capacitance, which can be written as capacitance is equal to Q divided by V. So the gradient of this graph is capacitance C. Now the definition of the capacitance. Capacitance is the ratio between charge and potential of a capacitor. So C is equal to the ratio between charge and voltage, charge and potential. This is measured in coulomb. This is measured in volt, and coulomb per volt is called farad, and it is represented by capital F. This farad is large unit. Usually capacitors are available in the market in microfarad, but we will convert for the numerical into farad. Now, this capacitance is the ratio between charge and voltage, but the charge and voltage both are directly proportional. So we can say that capacitance is independent of charge and voltage. It is only defined from this graph, only calculated from this graph, but it does not depend on the charge and voltage, because when voltage becomes double, charge becomes double, so the double cancelled, the answer of the capacitance will remain same. Then it depends on, so the capacitance C, number one, depends on the surface area of the plates, because the charges are stored by the plates. So it depends on the surface area of the plate, but how? Directly proportional to A. Capacitance of the capacitor directly proportional to surface area of the plates. And number two, separation between two plates. Okay, so the separation between two plates, how? C is inversely proportional to separation D. Larger the separation between the plates, smaller the capacitance. And number three, it depends on the nature of insulator between the plates. But in A level, it is fixed, free space, vacuum. And its nature, its permittivity is represented by epsilon naught. So we can write the formula, capacitance is equal to epsilon naught A divided by D. Now move back to this graph, which is Q against V. If the area of this triangle is calculated, it becomes area is equal to 1 by 2 base into height. Look, charge multiplied by voltage is the energy. So the area under this graph will be equal to energy, which can be written as half QV. It means during charging, the battery is supplying energy E, QV, but the capacitor is storing half QV, mean the rest half of the energy is lost, as heat due to internal resistance of the battery and connecting wires. So the formula for the energy will be 1 by 2 QV. So this is the energy stored by the capacitor. What we have done, that Q is equal to CV. So energy is equal to 1 by 2 Q is CV into V. Replace this Q with CV. So the new formula will be 1 by 2 CV square. And if this equation is written like this, V is equal to Q divided by C, then this formula can also be like this, 1 by 2 Q, replace V with Q by C. So energy becomes equal to 1 by 2 Q square over C. So these are the three relations for the energy. Number one is energy 1 by 2 QV. Number two, 1 by 2 CV square. And number three, half Q square over C. Now look, all are half in 50%. Suppose while charging, length of the wire is L and the current average supplied is I, resistance is R, and the time taken for the charging is T, then the energy lost E is equal to I square RT. This is the loss of energy. Now, if we decrease the length by 2, it means the resistance also decreases. Same battery will send more current. So the capacitor will take less time to charge itself due to the double current. Then how much energy is lost? Look, it is I square RT, but the new value of the current is 2I. New resistance is R by 2, and the new time will be T by 2. So 4I square times R by 2, T by 2, 2, 2, 4 cancelled. So in all cases, the loss of energy will remain same. So we can't improve the efficiency of the capacitor. So half of the energy is lost in all cases. Now suppose capacitor is fully charged. It is disconnected. It is isolated from the circuit. Disconnected from the circuit. Total charge stored on the each plate is Q. Total potential V. Its capacitance C. And energy stored by the capacitor is E. And initially it has separation between the two plates is D. Now, if the separation between two plate is increased to the double value, so this will has direct effect on the capacitance, right? The C becomes half because the capacitance is inversely proportional to D. When D becomes double, capacitance becomes half. There is no leakage of the charges. Charge on the both plate will remain same because it is disconnected from the circuit. So due to the half capacitance, charge remains same. But formula is Q is equal to CV. When charge constant, then C and V both are inversely proportional. Mean when C becomes half, then the voltage on the capacitor becomes double. Now, when the voltage becomes double, look at the energy, which is 1 by 2 QV, charge constant, half constant, energy directly proportional to V. So initial energy E, but now it becomes double. So just by increasing the separation of an isolated capacitor, fully charged capacitor, we can increase its energy. But what is the physics behind the work done in increasing the D is stored as energy in the capacitor. So this is the reason for the increase of the energy of the capacitor. The work done on the plates to increase the separation is stored as energy, hence energy becomes double. But if this capacitor is remain connected in the circuit after charging, it is not disconnected from the circuit. Now it is once fully charged, Q, voltage V, capacitance C, energy stored E. Now this gap D is increased to double. Capacitance becomes half. So the capacitor has less capacity now. It will send few charges back, right? Because when the capacitance decreases, potential increases, so the capacitor will be at the high potential, battery becomes at the low potential. Due to the high potential, charges will flow back. So at the end, when the potential remains same, then there will be no flow of the charge. Initially, charges will flow because initially the voltage of the capacitor becomes greater than the battery. Now the charges are flowing back, and after some time, when both potentials are same, then the charge stops, right? It means before and after the charge remains same. Before increasing the D and after decreasing D, after some time after increase in D, the potential of the capacitor and the battery becomes same. So V becomes same. So Q is equal to CV. When V same, Q directly proportional to C. It means initially charge Q, so half is lost. So Q is equal to CV. So Q becomes half. Now what happens with the energy? Look, energy is equal to 1 by 2 QV, V constant, half constant, energy directly proportional to Q. When Q becomes half, energy becomes half. So instead of the increase, energy decreases to half. So when this capacitor is connected in the circuit and distance increases, instead of increase in energy, there will be decrease in its energy. So don't use any electric device while connected in the charging unit. If your cell phone is charging, it is a charging mode, don't use it. Otherwise, there is a huge loss of energy. Look, instead of becoming double, it is becoming half. So what is the difference between double and half? 4 times loss. Next, capacitors in series and parallel. So first, suppose series. Suppose we have 3 different capacitors, different values, and they are connected in series. This capacitance C1, this is C2, this is C3. And according to the principle, in series, current remains same. It means the charge on the plates of the capacitor remains same. Suppose 4 positive charges, then 4 negative charges, 4 positive charges, 4 negative charges, positive 4, negative 4. So the charge on the capacitor when they are connected in series will remain same, but voltage, potential will be different, V1, V2, V3. Now, according to Kirchhoff's second law, the total potential supplied is the sum of the all potentials across the resistors, across the capacitors. And then Q is equal to CV. So V can be written as Q divided by C. So this total voltage is total charge divided by C, capacitance total. This V1 will be Q1 over C1. This is Q2 over C2, Q3 over C3, but all Qs are same in series. So we can write this Q divided by C, Q over C1, Q over C2, Q over C3. So Q divided by C total, Q take common, 1 over C1, 1 over C2, 1 over C3, cancelled. So the total capacitance in series is 1 over C1, 1 over C2, 1 over C3. So it is totally opposite to the resistor formula. So hence, in series, capacitance decreases. In series, capacitance decreases. Now move to the parallel combination. Suppose 3 capacitors are connected in parallel. They have different capacitance, suppose C1, C2, C3. And this is a junction. So current is coming I1, I. This suppose I1, this is I2, I3 during the charging. So due to different current supplied, different charges Q1, Q2, Q3, but in parallel, voltage remains same. So according to Kirchhoff first law, sum of the currents entering the junction is equal to sum of the currents leaving the junction, which is also the law of conservation of charges. So the total charge supplied by the source is Q1, Q2, Q3. Now Q is equal to CV. It will be C1 V1, C2 V2, C3 V3. So C into V, C1, voltage in parallel same, C2V, C3V. So CV, V common, C1, C2, C3. So we cancelled. So the total capacitance in parallel is C1 plus C2 plus C3 and so on. Hence, in parallel, capacitance of capacitors increases. In parallel, capacitance increases, and in series, capacitance decreases. Now look, when Q is equal to CV formula, this voltage constant in parallel, so Q directly proportional to C, mean large capacitance capacitor will get more charge. Capacitor with large capacitance value will get more charge in parallel. And here in series, the charge will remain same because in parallel, current remains same. Okay, next. When capacitor is charged, it is connected with other capacitor series are parallel. Capacitance will be different. Total capacitance will be different. In parallel, it increases. In series, it decreases. Now, discharging of the capacitor. Suppose this is a capacitor which is fully charged. It is connected with a switch and a resistor. So capacitors are always discharged across the resistor. Okay, when the switch is closed, this capacitor is at the high potential, resistor at the low potential. So the current flows from high potential to low potential. So this is positive terminal. This is negative terminal. Electron will flow in this direction, but the current will flow in this direction. And the rate of flow of electron depends on the resistor value, because this resistor is controlling the current. Larger the value of the resistance, smaller the current, so the longer time to discharge the capacitor. So it means the discharging time of the capacitor directly proportional to resistance across which it is connected. This T is the discharging time. Large value of the resistance, small current, longer time will be taken for the discharge. And this T is equal to constant C into R in discharge time is the product of capacitance and resistance. Now, the capacitor charges non-uniformly, so discharges non-uniformly, mean exponentially. Suppose this is a time, this is the voltage, and this is the voltage of the fully charged capacitor V0. When it is connected across the resistor, this voltage gradually decreases. Now, this graph depends on the value of the resistance. If the resistance value is small, then the graph will be this. When large resistance connected, this graph. When small resistance, this was. Because T and R directly proportional. Small resistance, small time. Large resistance, greater time. But if capacitor is short-circuited, mean its terminals are connected with each other without any resistance. Suppose this is the capacitor, and these terminals are connected with each other without inserting any resistance, no resistance. So it will take short time, it discharges suddenly, which is called the short circuit. So the discharging of the capacitor occurs across the resistor. Time of discharging depends on the resistance. Negligible resistance, negligible time taken, huge amount of the energy is released with in small time. But when large resistor is connected, so it will take longer time to discharge. And this discharging time is exponential. So when we have to calculate this voltage, suppose at this time, so we will use the exponential graph, which is V over V naught, e power minus T over RC. This RC is actually the total time taken for the discharge, and this T time required for this voltage discharge. Initial voltage is V naught. For whole voltage discharge, this time taken is RC, but up to this voltage, this one, this is the time. And similarly, Q directly proportional to V, because the capacitance is constant. So this ratio is also Q divided by Q naught. So the capacitor discharges exponentially, non-uniformly. Now suppose we have three capacitors which are identical, and their capacitance is same. And each capacitor has V maximum 6 volts suppose. After 6 volt, it is short circuited. It can't bear the voltage above 6. This is a maximum safe voltage. Now the question is, if three identical capacitors are connected like this, what is the safe working voltage? Look, this can bear 6 volt. Now the problem is with this. We can draw the circuit like this. This is C. Now both are parallel. So they can be replaced with a single capacitor of 2C value, because in parallel, capacitance increases and series capacitance decreases. Now, they are in series, this capacitor, this double capacitance capacitor in series, charge remains same. When the charge constant on the both, then C is inversely proportional to V. Capacitor with large capacitance will get the small potential. So its maximum safe voltage is 6, but this capacitance is double. So its maximum safe voltage will be the half 3. So the total safe voltage between A and B then 6 plus 3, 9 volt. So this 9 volt is the maximum safe volt.